Hi, I'm Utsha Bhattacharya. I'm doing a project on face recognition using Eigen faces for my course EEL 6825 pattern recognition. So why exactly is face recognition needed? Mainly for security purposes. So what do we do generally? We distribute ID cards, RFID cards, but is that enough? It's not, right? Because what if it lands in the hands of an unwanted person? So we need an additional security, right? So here, face recognition comes to our rescue. Moreover, for biometric authorization, for passport verification, SSN cards, online banking, criminal investigation, name any field, and face recognition has a major role to play. So we need to study more about face recognition and talk more about it. So jumping onto the concepts of its implementation, we'll first discuss about principal component analysis. So what exactly is that? It's basically a very useful statistical tool that extracts out the most prominent features from a distribution of data. So here in this project, what we mean by data is face images. So PCA extracts out the prominent features out from them, and moreover, PCA can deal very efficiently with high dimensional data. So how does it do that? We'll talk about it later. So coming to Eigen faces, one of the other major concepts in this project. So in the field of computer vision, whenever we talk about eigenvectors, we refer to them as eigenfaces. As we learned from PCA, we extracted out the most prominent features from a face image. So what exactly is that? In mathematical terms, we can say that these are the eigenvectors of the covariance matrix of the data set of face images. So these eigenvectors basically record the variances between the different face images, the differences among them. So these eigenvectors are called eigenfaces, and as you can see from the picture, they look rather ghostly. Moreover, how can we perform face recognition using this approach? It broadly consists of two steps: training the recognizer, face detection, and recognition. So how do we train the recognizer? First, we gather a training set of M images of dimension n by n. So once we have done that, we'll transform each image into a face vector of dimension n square by 1. So once we have done that, we'll normalize the face vectors. What do we mean by that? We calculate the average face vector and deduct it from each of the face vectors. So what is the significance of this step? So basically, we deduct the common features from each of the face images in the distribution set and in the training set, and all the images in the training set are now left with only their characteristic features. So now that we have done that, it's time for us to calculate the eigenvectors. For that, we need the covariance matrix. As we know, it's equals to AA transpose. What is A? A is actually a matrix constituting the normalized face vectors. As we can see from the slide, C is going to have a huge dimension, that is n square by n square. Finding out the eigenvectors from such a huge amount of data, that is going to consume a lot of computational time. So we need to think of an alternative approach, right? So that is why we have taken another matrix equals to A transpose A, which is of dimension m by m, the m by m, right? So the dimension is reduced drastically. Finding eigenvectors from L is going to take lesser time, and we have seen that from mathematical deductions that the eigenvectors of C and L are almost the same and are related by the given formula. So now since we can easily find out the eigenvectors of L, we can map it to find the eigenvectors in C, which is of dimension n square by n square. So here, using a smaller dimension, I'm able to find the eigenvectors in a larger dimension. So the dimensionality reduction really helped us. Now that we have found the m eigenvectors of C, C will keep only the k most prominent eigenvectors. Why do we do that? Because according to the principles of PCA, the first eigenvector is going to have the most relevant information stored in it. The succeeding ones will have lesser amount of information stored in it. That is why, as we can see from the picture, the first few of them are more rich in information and the last few contain noise, more noise, so we discard them. So now that we have found the k most prominent eigenvectors, it's time for us to represent each image in the training set as a weighted sum of the eigenfaces and the mean phase. So as we can see from the picture, the first eigenphase has a contribution of W1% to the face image. The second eigenphase has a contribution of W2% to the top image. So like that, we can form a weight vector for each of the face images. So now that we have trained our recognizer, it's time for us to perform the most important function, that is recognize an unknown face. Once we first input a face image, we converted the face image to a phase vector like we have done before, and once we have done that, we'll normalize this phase vector. What do we mean by that? We subtract the mean phase vector from this input phase vector. Once it's done, we'll represent the input phase vector as a weighted sum of the k eigenfaces. This will give us a weight vector for the input phase image. Once we have got the input weight vector for the input image, we'll calculate the distance between the weight vector of the input phase image and the weight vectors of all the images in the dataset. If the distance is less than the threshold, then bingo, it's a good news, though it's a known person. But if it's not, then we have an unauthenticated person. So while working with this project, I've noticed a few benefits of using eigenfaces. One of them is definitely simple and easy to code, and it can also handle large data sets. Another thing that I've noticed is that once the eigenfaces for the entire dataset is calculated, face recognition can be done really quickly in real time. So, and other major things to notice in this implementation is that eigenfaces do not consider features as do not extract features based on our usual notion of facial features like nose, eyes, etc. It will take into consideration a global feature like the human face as a whole. So for this project, I've used the ADNT dataset. It roughly consists of 400 images of 40 individuals, and each individual has 10 images, all of them taken in different poses, like some of them smiling, some of them winking, happy, sad, angry, some of them with glasses, without glasses. So basically different poses. And one thing to note here is that all the images were of same size and were taken against a dark background and with varying light conditions to test all possibilities. So now it's time for our demo. So first we'll have a look into the images folder. So it has two folders. Gallery contains the training set of images and probe contains the images that we'll test against. So I've already trained the recognizer. Now it's time for me to show you how the recognition is performed. Let me choose Amber 2 from the probes folder. Okay, I'll keep the threshold as 2 and eigenfaces as 6. These are the two inputs that I must give in order to perform this project. Okay, so it's a match, and as we can see, the two images were different and the recognizer has recognized correctly. Now let us try with a different one. Let's try with Jill. Yeah. So this time I'll keep a rather low threshold in order to just test. Let's see what happens. Okay, so no match. So that's great. Our recognizer has performed successfully. So let us have a look at the eigenfaces that were formed in this experiment. Okay, as we can see, it looks really scary and it looks rather ghostly. So with this we come to an end of our presentation, and thank you. I'll just end this demo.